Welcome to the talk on energy flow and complexity in the cosmic phase. We'll be looking at the cosmic web, galaxy formation, star formation, and formation. So complexity in the cosmic phase starts with a Big Bang. We already heard Andre talk about this as rapid cooling due to expansion, forces unfold, particles bind, energy steps scale by about a factor of 1,000. In the intermediate phase, structure formed, and that's where we're going to be taking a look at. So this diagram on the right, which we'll have a little bit, it starts with a Big Bang, and we'll be looking at this middle part here where the structure forms. There also were size relationships, even recognized in the early 1930s when these sizes were first really recognized, is that there seemed to be a strange coincidence between the large sizes and the small physical constants. And later in the 1970s, this was more formalized by people like Rees, Press, and Lightman, and Carr into estimate of the sizes based on just a few of those parameters. So let's take a look at this, kind of the history of the universe, kind of from the left-hand side with the Big Bang. I already talked about the early part of it. The formation here, the purple is the dark matter, which was able to form first because the regular matter was ionized and so didn't really have collapse until it was neutralized. And so until it cooled down a little bit further, but once it cooled down, it could follow the dark matter and form the structures, the cosmic web, and then go further into clusters of galaxies and solar systems and planets. And so in the very beginning, there was the unfolding of these forces, and I'd like to view this because some of those forces had some excess energy that could be expended later. So first of all, we had gravity, which is a long-range attraction to make structures. There's no neutralization of it. The more mass you have, the greater the force. Electromagnetic is also a long-range attraction. However, it is neutralized by positive and negative charges, for example, in the atoms. It is long-range because we can see light from millions and billions of light years away in stars. But when it neutralizes, it leaves many secondary phenomena, such as chemical bonds, light interactions, and phase changes that are, most of what we observe in our daily lives. The strong nuclear force binds things together, and so they generate a lot of diversity, as talked about by Tyler Volk in there, so that gives us all those elements. The weak nuclear force is not as well known, but one of the major impacts of it is that it slows down the process of the converting the nuclear energy in the stars. And so if this were not as weak, the sun would not live as long and probably life not be able to form either. And so there's two of these forces that leave a lot of energy after the Big Bang. One is the gravity, because things are kind of spread out. And we know that as things fall under gravity, they gain energy. Other one is a strong nuclear force because even though in the early Big Bang some hydrogen fused to helium, not much of it did, and there's still a long way to go to the lowest energy nuclei, which is iron. And so Eric Chaisson had looked at both the early phase and then the phase on Earth, the terrestrial phase in this, and that the energy flow is important per mass. The system flow might be important. Efficiency is important. For example, the brain can work on 20 watts, and we show here the energy rate density being joules per second, which are watts per kilogram. So a brain with 20 watts, 1 kilogram would kind of match right around here. And so there's the difference of the cosmic and terrestrial phases. And so, the early part was just the particles, which were self-organizing structures that had no energy flow. And then the later structures had no agency, and that's what we're taking a look at, but had energy flow, dissipative physical structures, so that's cosmic web, galaxy, stars, and planets, along with the large energy flows of gravitational and nuclear potential. So this has been looked at a little bit recently. And so Chaisson looked at the energy flow density, and it leads to more complexity. That is, more and more complex structure needs more and more energy flow to keep it away from equilibrium, to keep it in order. Modis also took the coffee mixing analogy with cream, kind of shown in the diagram below, where you have black coffee on the left and you have coffee mixed with cream on the right. And so the entropy increases as you go from ordered state of two different things to one where they're well mixed. However, the complexity is more important kind of in the middle where there's interesting structures to take a look at. So you can see that the complexity is related to the rate of change of the entropy. So during the cosmic web, there were dark matter that starts the structures. Some have compared it to things like origami folding, where the folds are where some of the galaxies kind of occurred, and there's some correlation between the spins and the orientations of nearby galaxies. And a lot of people do various simulations, and there's tremendous energy flows in there, right, between the voids and where the matter kind of is leading to. And so there's a lot of these simulations out there that have led to predictions kind of and match well with the measurements of the relative frequencies of different types of galaxies. And so, as I mentioned before, when galaxies, it is not a matter equilibrium. There's flow into that galaxy from the cosmic web, and there's energy flow outside of the galaxy when the central massive black hole is active, so active galactic nuclei, and there's energy flow in there, and then there's jets going to the outside. So not everything falls into the black hole. Some of it is ejected from the galaxy itself. Already mentioned the relative frequency of the different types of galaxies. And in the galaxy, there's many different structures, right? So the central massive black hole, the halo, the arms, dark matter halo, the stars, and the gas clouds in there. In stars, there's multiple generations. Some of the second generation stars are still around, but the first generation were usually large mass with mostly hydrogen and helium, and they were relatively short-lived. And then the cooling of gas leads to heating, and so the gravity is so backwards in that particular case, having a negative heat capacity. And you might have thought that stellar formation has continued in galaxies kind of at the same pace throughout, and as I found out, that's not true. There was a stellar peak formation about 4 billion years after the Big Bang. So the Big Bang is on the right here, and if you look more towards today, you see it peaking about 10 billion years ago, or about 4 billion years after the Big Bang. Remember that the sun formed about 4.5 billion years ago, so much later than the stellar formation peak. Also, in stellar fusion, it's not just that the star has regular burning, which, for example, in the sun is mostly the hydrogen burning now, but in a star with 25 solar masses that will eventually become a supernova, the hydrogen burning only lasts for 10 million years, and the helium burning lasts for 1 million years, and so on, with somewhat equal factors going down all the way down to the silicon, which burns into iron, and eventually nothing's left, and so it goes into the supernova phase, releasing all those materials. And it's somewhat of a singularity type of formation. Hopefully, this looks somewhat like civilization, with the energy rate kind of increasing over time and shorter time scales, and let's hopefully the analogy does not continue all the way to the end. So in terms of planets, Chaisson had used atmosphere for the FERD with energy from the sun. But actually, if you look at the Earth, the energy inside the Earth is the heat inside. Two contributions from that: the original gravitational potential and also the nuclear potential from the supernova radionuclides that are left in there. They're approximately equal, and so there's a flow outside. If you compare that to the mass of the Earth, it's a very small compared to anything on his time scale, but it's very important. Right? The fact that the Earth's center is hot leads to the magnetic field, which shields a lot of the life on the planet from cosmic radiation. It also generates plate tectonics, which has the cycling of elements and formation of land and those things. So it's very important, but the whole energy flow of the planet is very small compared to other energy flows, either in the life processes on Earth or compared to other cosmological objects. And so the formation of the Earth is also a little bit different, right? It's not a regular gravitational collapse because, it's not the hydrogen and the helium that are collapsing, which dominate the mass, but it's rather the metals that can form chemicals and kind of stick together. That is important, especially for the rocky planets. So I looked at what other physical systems do, and so there's formation of vortices, which is seen at the top. And so in turbulent flow, you have these formation of structure. You can see the structure for more and more complexity as it moves on in time. Down below on the left is also more irregular type of turbulent flow. And so maybe we can make the analogy to the universe in that way, that it starts out very simple, and then as time progresses, it forms more and more structures, because in the formation of these two at the large scale, there's not much chance to have energy deposit, transfer, or flow into the system. It actually has to form structures, and then more and more flow, heat can be transferred to the system as viscosity becomes important in here. So this is what happens in physical turbulent systems. And I found that there was a paper by Hogan in 2001 looking at the energy flow in the universe and various channels of energy flow from the Big Bang, from dark energy, from gravitational collapse, stars, active galactic nuclei, gravitational waves, supernova, and gamma ray bursts. And he looked at the luminosity, the duration, the rate, the number of active ones in the whole universe, and then found out the total power that they were being generated, ergs per second. You compare that with the mass of the ordinary matter in the total universe, and this comes to about 10 to the minus 7 watts per kilogram, very similar to the lower estimates of Chaisson for example, the galaxies. And so what was kind of impressed Hogan here is that these are very similar, right? You might expect that over all these orders of magnitude of different sizes and times, that the total power might be quite a bit different. And so what he had at the end of the paper is that this shows a remarkable coincidence that despite of the 20 orders of magnitude of variation, the integrated power is comparable. There looks like there might be feedback loops controlling the release of energy. There's some type of choreography. And so even though, everything is going from fundamental physics, there's some cosmoecology going on that might be going on. And I found some later writings on that. This is a paper from 2019 on the impact of the connectivity of the cosmic web on the physical properties of galaxies at its nodes, and it's being looked at. There's also a lot of people looking at the connections between the active galactic nuclei and stellar formation. There's very interesting correlations in there. This was from a very international team and continued to look at it mostly through simulations and then comparing to the amounts of data that are being collected from astronomical satellites. So when we look at the energy flow over time, we can see that it starts with a cosmic web and then structures form, right? And so the universe's structure is becoming more complex as kind of these, turbulence occurs and going to smaller scales. And it's not that the new structures are becoming more complex than the previous. That only occurs in the later phase with complex adaptive systems that Chaisson had looked at. So I think we can say that, galaxies are more complex than stars. I mean, they contain stars and they contain everything else, and that there's more energy flow within the total galaxy than in the stars, but we can see these equal contributions and people really looking into this as to what the relationships between these are. So in conclusion, we explored some of the cosmic energy flow, physical complex dissipative systems by looking what others had done, comparing that to what Chaisson had mentioned in his work on FERD. We include cosmic web galaxies, active galactic nuclei, stars, supernova, gamma ray bursts, gravitational waves, and planets. And it looks like more of a cascade as the universe turbulence evolves to smaller scales. Hogan reports that each level of turbulence opens up an energy flow channel, supports about the same amount of energy flow, and others are looking into that possible connection. And so we can view the universe as developing more complexity as the structures evolve, not that the new structures have more complexity. Thank you very much for your attention.